there's a cosmic enigma out there, a comet that, by all conventional understanding, simply shouldn't exist. We call it 3I Atlas, an interstellar visitor that arrived on our celestial doorstep, bringing with it a cascade of unsettling contradictions. And now, fresh data, released on October 14th, 2025, from the Transiting Exoplanet Survey satellite TESS, doesn't just collaborate this anomaly, it intensifies the mystery, suggesting a deeper, more profound departure from what we thought we knew. This new information, drawn from an exhaustive analysis of over 9,000 images, doesn't merely refine our understanding, it tears open the lid on what appears to be a deliberate suppression of critical details, a scientific blackout that warrants immediate, uncompromising scrutiny. Tonight, we will unspool this meticulously gathered evidence, laying it bare to finally, unequivocally settle this baffling celestial puzzle. But the unravelling of Atlas is not the only thread we follow into the cosmic dark. We also delve into the unnerving rhythm of a mysterious star, ASCAP J1D2US, Sunai 11, an object that pulses with a precise, almost artificial 44-minute heartbeat in both radio and X-rays. Its existence defies current astrophysical models, forcing us to ask, is this a new, bizarre entrant to the pantheon of cosmic oddities, or something far more profound? We will explore this unprecedented phenomenon, dissecting its implications for our understanding of stellar evolution and fundamental physics. Beyond these profound galactic mysteries, we cast our gaze closer to home, examining the imminent arrival of 4 coronal mass ejections hurtling towards Earth. Their anticipated impact this week promises not just spectacular auroral displays, but also significant disruptions, potentially adding another layer of complexity to our attempts to observe and understand these distant enigmas. Finally, we journey to the very edge of theoretical possibility, to the realm of the ghost particle, a neutrino of such unimaginable power that it shattered every existing record, crashing into our planet with an energy level once deemed theoretically impossible. This single event, a cosmic bullet from an unknown accelerator, challenges the very fabric of our high-energy physics models. Stay with me, because what we are about to uncover, what we will piece together from these seemingly disparate threads, will fundamentally reorient your perception of the universe, and perhaps more unnervingly, what silent observers might be watching us from its impenetrable depths. If these unfolding mysteries grip you as intensely as they do me, if the pursuit of truth behind the veil of the unknown resonates, then ensure you hit that like button and subscribe. Your engagement fuels this journey of discovery, guaranteeing you don't miss a single update as these stories evolve in real time. Share your thoughts, your location, the time you're tuning in, and critically, whether you believe we're truly receiving the full, unvarnished truth about these paradigm-shifting discoveries. To help this community thrive, extend this broadcast's reach across X, Facebook, Reddit, or simply your group chats. You are the driving force behind our relentless chase for these narratives, and for that, I offer my deepest gratitude. Part 1. TESS says, no tail. Why that breaks the simple comet story. Imagine the night sky, not as a poetic canvas, but as a meticulously monitored laboratory. Hundreds of instruments, each a triumph of engineering and scientific ambition, ranging from multi-million-dollar ground-based observatories to spacecraft silently navigating the vacuum of space, all converged, their collective gaze fixed on a single, accelerating object within our solar system. Now, picture the most exquisitely sensitive of these instruments, a purpose-built detector designed to discern the faintest celestial whispers. After meticulously co-adding over 9,000 individual images, delivering a verdict that no one, absolutely no one, anticipated, it declared, with chilling certainty, there is no tail. This pivotal declaration arrived on October 14th, 2025, when astronomers unveiled the initial findings from a colossal data analysis conducted using TESS, the Transiting Exoplanet Survey satellite. Their focus was 3I Atlas, an interstellar interloper that has been a source of profound scientific bewilderment since its initial detection. The TESS team had meticulously collected over 9,000 frames of Atlas, employing a sophisticated image processing technique known as co-adding. This method is specifically engineered to extract incredibly faint signals from overwhelming background noise, effectively amplifying the presence of even the most subtle celestial features. Think of it as repeatedly replaying an almost inaudible melody, each repetition increasing the volume until the lyrics, or in this case the hidden structures, finally become discernible. What TESS did not find, or rather, the stark absence of what it should have found, was nothing short of extraordinary. The object presented itself as a perfect point source, a mere dot against the cosmic backdrop. There was no extended coma, no diffuse envelope of dust and gas visibly billowing outwards, and most critically no iconic tail streaming away from the sun. When radial brightness profiles were meticulously measured, analysing how light intensity diminishes as one moves away from the object's centre, the light curve plummeted precisely like that of a distant star, not the characteristic gradual decline expected from a comet. Stars, by virtue of their immense distance, are observed as point sources. Their colossal dimensions collapse into a single pixel. Comets, conversely, are fundamentally different. They are defined by their dynamic activity, the sublimation of ice, the ejection of dust and gas, the visible manifestation of an extended coma, and of course, the dramatic tale that has inspired both awe and dread for millennia. The point spread function, or PSF, is the unique optical signature a telescope imprints on a point source. Every telescope possesses a distinct PSF akin to a fingerprint. When TESS scrutinised 3I Atlas, it registered only this unadulterated PSF, nothing beyond it. The analysis team were able to rigorously quantify the implications. Had there been dust exceeding a specific surface brightness threshold, even subtly, the stacking process would have revealed it. This co-adding technique enhances the signal-to-noise ratio to such a degree that even the faintest features become unequivocally detectable. From this, they derived stringent constraints on dust density, particle size, and ejection velocity. Every numerical indicator converged on the same inescapable conclusion. Whatever dust might be present around Atlas, it simply wasn't behaving in any manner consistent with typical cometary dust. Yet, this is where the narrative descends into truly perplexing territory. Other sophisticated observatories paint an entirely different picture, one that directly contradicts TESS's stark finding. The James Webb Space Telescope, JWST, observing in infrared wavelengths, has unambiguously detected water vapour and carbon dioxide around 3I Atlas. Its spectroscopic measurements unequivocally reveal mass loss, volatiles actively escaping into space. These are the quintessential signatures of intense activity, precisely what a comet does. But if this is indeed a comet actively expelling material, then where, precisely, is the tail? Where is the tangible, visible evidence of all this material streaming away, reflecting sunlight? This observational dichotomy forces us into an uncomfortable corner. Either the coma around Atlas is so extraordinarily compact, so unnaturally dense and gravitationally or electromagnetically confined, that it remains invisible to optical telescopes, even as it generates detectable gas signatures, a phenomenon for which we currently have no natural explanation. Or, and this is the more unsettling possibility, what we're calling a comet isn't a comet at all. It's akin to witnessing a roaring campfire but seeing no smoke ascending. Either the smoke is being compressed into an invisible state by some unknown mechanism, or the fire we're observing is not in fact fire. This unavoidable contradiction sits at the heart of the Atlas mystery. TESS dedicated months, its unparalleled sensitivity focused on this object, designed precisely for detecting faint extended structures. It saw nothing. But other instruments, meticulously tuned to different wavelengths and thus sensitive to different physical processes, are loudly proclaiming that something is undeniably occurring. One of these observations is fundamentally flawed, missing a crucial element, or our entire established framework for understanding what a comet should look like, how it should behave, is about to shatter. And here's the unsettling truth that permeates scientific discourse around this object. We have witnessed comets exhibit unusual behaviours before, but never this. Never an object that so perfectly mimics a stellar point source, while simultaneously broadcasting unequivocal chemical signatures of vigorous, ongoing activity. The numbers don't merely fail to reconcile, they actively, vehemently contradict each other. This isn't a minor discrepancy attributable to varying observing conditions or instrumental quirks. This represents a fundamental disagreement about the very nature of the object's activity. The TESS data is now public, accessible to anyone who wishes to download it, perform their own analysis, and verify the numbers. The results are demonstrably reproducible. The no-tail finding is scientifically robust, which means the imperative now is to explain it. Because if we cannot account for this with conventional comet physics, then we are compelled to begin considering explanations that sound uncomfortably, perhaps even outrageously exotic. But before we venture into such speculative territory, we must first thoroughly comprehend the depth of these contradictions and why different instruments are painting such wildly divergent portraits of the same celestial visitor. Part 2. Cross-instrument contradictions, JWST, ground arrays, spectrographs. Let's zero in on the James Webb Space Telescope, that $10 billion marvel of infrared astronomy, as it meticulously swivels its golden mirrors towards 3i Atlas. The observations that stream back are unambiguous. Abundant carbon dioxide, significant water vapour, a gaseous coma undeniably rich in volatile compounds. Its spectrographs are exquisitely sensitive, picking up distinct molecular signatures, emission lines that indicate atoms are being excited, molecules are vibrating, gases are actively flowing outward from the nucleus. This is the unmistakable soundtrack of cometary activity, loud and clear in the infrared. Yet, simultaneously, ground-based optical telescopes report a starkly different visual reality. Some detect faint asymmetries, vague hints of extended structure, while others, equally precise, register almost nothing at all beyond a pristine point source. Different instruments, different stories, different physical truths. The question is, what accounts for this profound divergence? The answer lies, in part, in the distinct physical phenomena each instrument is designed to measure. JWST, operating in the infrared spectrum, is uniquely attuned to the thermal emissions of molecules as they vibrate and rotate. It is astonishingly sensitive to gas, to the intricate chemical composition of the material wafting around the nucleus. It doesn't require reflected sunlight to detect coma. It's listening to the complex melodic singing of molecules in the infrared, and those melodies are, for Atlas, remarkably strong and clear. The Sphere-X mission, another advanced infrared observatory, has corroborated these findings, reporting substantial quantities of vaporized carbon dioxide around Atlas, with CO2 to water ratios that are highly unusual, even when compared to other weird comets. This hints at a unique, perhaps primordial composition. Optical telescopes, however, function on an entirely different principle. They are designed to observe reflected sunlight, specifically how dust particles scatter the sun's light back towards us. To resolve structural features in an optical image, there must be extended dust, particles dispersed over a sufficient volume of space, capable of intercepting and redirecting sunlight. If the dust is too compact, too tightly bound to the nucleus, or if the individual particles are of an inappropriate size to efficiently scatter optical wavelengths, then an optical telescope might register very little, even if copious amounts of gas are actively venting from the object. This is where the complex science of scattering functions becomes critical. Micro-sized dust particles, on the order of microns, scatter visible light with high efficiency, forming the familiar luminous tails. Larger particles, ranging from millimeters to centimeters, are less efficient scatterers and, possessing greater mass, are harder to accelerate away from the nucleus. These larger grains might hover in a tight envelope close to the object, creating a compact yet optically faint shell that optical telescopes struggle to resolve. Yet even in this confined state, ice sublimating from their surfaces could produce abundant gas, precisely what JWST detects. Then there is the issue of observation geometry, specifically the phase angle, which defines the angle between the Sun, the object, and the observer. This angle dramatically influences how any tail or coma structure is perceived. If our line of sight places the object at an unfavourable phase angle, a tail could appear severely foreshortened, pointing almost directly towards or away from us, rendering it effectively invisible despite its physical existence. Different instruments, operating from different orbital positions and at different times, will necessarily view the object from varied angles. A tail perfectly visible to one might be geometrically obscured from another, a purely circumstantial bad luck scenario. Cross-instrument disagreements are not unheard of in astronomy. Comet Earson in 2013, for instance, was initially predicted to be a spectacular display, but ultimately disintegrated, with different telescopes reporting vastly different levels of activity at various times. Similarly, C2017 K2 showed an extended coma in some observations but appeared quiescent in others, sparking debate about intermittent activity. The critical distinction with Atlas, however, is one of scale and binary nature. It's not merely exhibiting variations, it's presenting a stark binary split, either a tail or no tail, either a point source or an extended object. There is almost no middle ground in the combined observations, creating a profound dissonance. Compounding this is the timing mismatch. JWST observes during specific targeted windows. Ground telescopes operate on their own schedules. TESS, while continuously staring, does so at a lower spatial resolution, optimized for detecting transient dimming. What if Atlas is not continuously active, but rather undergoes intermittent bursts of dust and gas ejection, akin to cosmic pulses? In such a scenario, one telescope might capture it during an active phase, while another, observing moments later, perceives only quiescence. The observations would appear contradictory, yet both would be accurately reporting the object's state at that precise moment. However, even when meticulously accounting for all these variables, composition, scattering properties, geometry, and intermittent activity, the sheer level of disagreement remains profoundly unusual. Deep stacking techniques applied to optical images from professional observatories are designed to recover even the faintest dust features. The fact that TESS, after combining thousands of frames, detects no extended structure, strongly implies either the dust is extraordinarily compact, or it is simply not present in the quantities that JWST's gas detections would lead us to expect. And if the dust isn't there, where is the copious gas originating from? Gas doesn't spontaneously appear, it sublimates from ice, either directly from the nucleus or from dust grains. Both processes inherently should produce dust. This leads to a disconcerting question. Can we trust any single instrument's narrative in isolation? Each telescope acts as a distinct sensory organ, faithfully reporting what its specific senses detect about this elephant in the cosmic room. But the composite picture, the unified image, is failing to cohere into anything recognizable or internally consistent. This is typically the point where most astronomical mysteries find resolution. More data is gathered, models are refined, a subtle, previously overlooked effect, perhaps unexpected scattering properties or an unusual compositional nuance is identified. Yet, with every new observation of Atlas, the picture paradoxically grows murkier, rather than clearer. And now we arrive at a critical, almost tantalizing possibility: the spacecraft question. There exists one specific instrument that might have possessed the perfect vantage point, the optimal resolution, the ideal geometry to decisively observe what 3i Atlas truly looks like up close. The Psyche mission, launched by NASA, was on its journey. Its trajectory might have brought it within viewing range. If it captured images capable of cutting through this web of contradictions, then the most pressing question isn't what they show, but where they are. Part 3, Timeline and the Psyche. Pivot, where Psyche fits and where the public record goes. Quiet. We have reached an impasse. Earth-based observatories and advanced space telescopes offer conflicting testimonies about 3i Atlas. Now, we must address what could be the single most crucial observation, one that, conspicuously, has not yet entered the public discourse. The Psyche spacecraft, launched by NASA with the mission to explore the metal-rich asteroid 16 Psyche, has been traversing interplanetary space, equipped with a sophisticated suite of imaging instruments. Its primary objective is its target asteroid, but as is standard practice for deep space missions, it routinely captures calibration images, navigation frames, and opportunistic scientific observations along its lengthy cruise phase. The spacecraft carries a high-resolution imager, perfectly capable of acquiring detailed photographs. Throughout its journey, mission teams regularly orient these cameras towards various celestial targets, not just for system testing and instrument calibration, but also to gather bonus science whenever a valuable opportunity arises. This is a common, well-established procedure for interplanetary missions. If you have a camera and you're navigating the vastness of space, you seize every chance to take pictures. NASA, to its credit, has publicly released some of these auxiliary images, calibration shots of Earth and the Moon taken from varying distances, starfields for navigation verification and the like. Here, however, the timeline of events becomes particularly intriguing. Based on publicly available ephemeris data, the precise positions and calculated trajectories of both the Psyche spacecraft and 3i Atlas, there existed specific windows of opportunity. During these periods, the interstellar visitor would have been within the potential viewing range of Psyche's cameras, not necessarily at a close-up high-resolution encounter, but certainly close enough that a targeted observation could have yielded invaluable data, potentially resolving the myriad contradictions. The exact geometric parameters are calculable from published mission parameters, confirming that the possibility of such an observation indeed existed. So, the critical, unanswered question looms: where are those images? NASA maintains extensive archives of raw mission data. The standard operating procedure for the vast majority of space missions dictates that their raw frames, or at the very least comprehensive metadata, detailing what was captured and precisely when, are eventually released to the public. These archives are the goldmine from which amateur astronomers sometimes unearth previously undiscovered comets or asteroids in decades-old images, and from which professional researchers re-examine data to uncover phenomena missed during initial analyses. The raw images from Psyche's instruments should be discoverable, residing either within NASA's sprawling planetary data system or in mission-specific archives. The profound mystery, the chilling silence, is that no public announcement has been made regarding the release of raw Psyche images that depict 3i Atlas during these closest approach periods. This absence could signify a multitude of things, and it is imperative that we exercise rigorous caution before succumbing to speculative conclusions. Let us first consider the most benign and entirely plausible explanations. Spacecraft data downlink is an inherently constrained resource. Deep space missions operate under severe bandwidth limitations, meaning they can only transmit a finite amount of data back to Earth during each scheduled communication window. Mission planners are therefore forced to prioritize what gets transmitted. Engineering telemetry, data crucial for monitoring the spacecraft's health and operational status, invariably takes precedence. This is followed by core science data pertaining to the primary mission objectives, and then, only if bandwidth permits, everything else. If Psyche's cameras did capture images of Atlas, those frames might simply be residing within the spacecraft's onboard memory, patiently awaiting a future communication window with sufficient bandwidth to be transmitted. Furthermore, considerations of data compression and management are always at play. Spacecraft possess finite data storage capacities. They frequently utilize ring buffers, which continuously overwrite older data as new observations are acquired. If images of Atlas were not immediately flagged as high-priority science, they might have been heavily compressed to conserve space, or, in a more regrettable scenario, even overwritten by subsequent observations. This occurs far more frequently than the public realizes. Not every single frame captured by a space mission makes it back to Earth in full resolution. Metadata and indexing errors present another entirely plausible explanation. The images might exist within the archive but are not properly catalogued. Incorrect timestamps, mislabeled target fields, corrupted headers. Anyone with experience in large-scale astronomical databases understands how easily data can become effectively lost, simply by being misfiled or attributed with incorrect keywords. An image of Atlas could theoretically be sitting in the archive, labelled as a generic calibration frame or an anonymous star field, simply awaiting a discerning eye to recognise its true content. Finally, there is the bureaucratic explanation. Space agencies, by necessity, implement embargo periods, strict data rights policies, and exclusive access windows for mission teams. It is entirely possible that these images exist. The Psyche mission team is actively engaged in analysing them, and their public release is simply scheduled for a future date that has not yet arrived. Science teams are routinely granted first access to their proprietary data before its general public release. This policy serves to protect the intellectual investment of the individuals who designed and constructed the instruments, allowing them time to publish their groundbreaking findings before others can scoop them using the same hard-won data. All of these explanations are perfectly rational, grounded in the realities of space mission operations. None of them necessitate invoking conspiracy theories or cover-ups. They represent the normal, predictable friction inherent in the complex execution of deep space missions. But here is the critical distinction that must be made. The absence of evidence is not in itself evidence of absence. We simply do not know what was captured because the complete archive remains inaccessible to the public. We are not privy to the decisions made regarding downlink prioritization, the compression methodologies employed, or the precise labeling protocols. The metadata that could illuminate these questions might itself be incomplete or deliberately withheld. What we can do, what we must do, is ask. Freedom of Information Act (FOIA) requests possess the legal power to compel the release of government-held data. Formal archive access requests can be filed for mission logs, spacecraft telemetry logs, and instrument activity reports, documents that definitively exist and are legally subject to request. The pivotal question is whether the images that could definitively resolve the Atlas mystery are patiently waiting in some archive, poised for discovery, or if they were never captured at all. Or, perhaps most unsettlingly, if they were captured and are being withheld for reasons we do not yet comprehend. This is where the narrative diverges, where speculation must give way to rigorous investigation. If these images exist and are released, we might, at long last, truly see what Atlas looks like, thereby reconciling the stark contradictions between TESS, JWST, and all other observations. If they do not exist, we must understand why a spacecraft with fully functional cameras failed to capture what could be considered the astronomical event of the decade. And if they exist but remain inaccessible, then we confront a fundamentally different problem entirely, one that directly challenges principles of transparency, and data governance within the scientific community, raising questions far beyond mere astrophysics. This is the crux of the matter, and the path forward demands both scientific rigour and institutional accountability. Part 4: Physical alternatives to comet, non-comet hypotheses that fit the data. Let's momentarily set aside the tantalising question of the Psyche archive and pose a more fundamental inquiry. What if 3I Atlas is not a comet in any conventional sense? What if we have been attempting to force it into an entirely inappropriate category from the outset, clinging to a classification that fundamentally misrepresents its true nature? If this object steadfastly refuses to adhere to established cometary rules, what other explanations, however exotic, could potentially account for its contradictory behaviour? And can any alternative hypothesis realistically survive the ever-growing pile of observational constraints we've amassed? Hypothesis 1. A large, inert body with micro-outgassing. Imagine a substantial chunk of rock and ice, originating from a distant stellar system, moulded by entirely different formation conditions than anything found within our own solar system. Perhaps it is predominantly inert, not actively sublimating with the vigour of a typical comet, yet still releasing minute quantities of gas. This outgassing could occur through microscopic fissures, through rare, localised pockets of volatile ice exposed on its surface, or through a network of internal voids. This model could potentially explain the gas signatures so clearly detected by JWST, without simultaneously requiring the massive dust production that would inevitably generate a visible tail. The object would appear compact, a perfect point source, while still exhibiting detectable chemical activity. The challenge with this model, however, lies in quantifying the gas production rates. JWST's measurements suggest a significant loss of volatiles. You simply cannot generate that much gas from microcracks without also, by the very physics of sublimation, entraining and ejecting a detectable amount of dust. Ice does not sublimate cleanly. It inevitably drags dust particles long as it vaporizes. This would necessitate a highly specific, almost impossible composition. Perhaps pure volatile ice somehow completely separated from any dust component, a scenario that appears geologically implausible. Hypothesis 2. A fragment cloud. What if 3I Atlas is not a singular cohesive object, but rather a tightly bound swarm of smaller fragments? Individually, these fragments would be too diminutive to resolve, even with our most powerful telescopes, but collectively, their combined brightness would account for what we measure. Picture it as a celestial school of fish, or a flock of birds, where the collective entity behaves as a unified whole. Each individual fragment might produce a minuscule amount of gas and dust, but this material could remain largely confined within the swarm, rather than streaming away in a classic expansive tail. This could elegantly explain the point-like appearance. If the fragments are clustered closely enough, beyond our angular resolution limits, we would perceive them as a single, unresolved object. The gas production would be distributed across numerous small surfaces, potentially creating scattering properties distinct from those expected from a single nucleus. However, this model also encounters significant difficulties. What mechanism would maintain such a swarm's cohesion? Over interstellar distances, without a substantial collective gravitational pull, the fragments would inevitably drift apart. Furthermore, a genuine swarm, even if unresolved, should exhibit some degree of structural variation, some subtle elongation, or a degree of fuzziness, even if individual components remain unseen. Hypothesis 3. Electrodynamic effects. Here, we delve into truly exotic territory. Suppose the dust particles encircling Atlas are electrically charged, and a magnetic or electric field of sufficient strength exists to actively retain them close to the nucleus. Charged dust can levitate, can be trapped in intricate configurations that defy simple ballistic trajectories. We observe analogous phenomena in planetary rings, in controlled laboratory plasma experiments, and in various astrophysical regions where electromagnetic forces exert dominance over gravity. If Atlas carries a significant electrical charge, or if it generates powerful fields through some unknown process, the dust might not escape into a visible tail at all. Instead, it could hover, circulate, or remain electromagnetically confined. The gas, being composed of neutral molecules, would still escape, as molecules are far more challenging to trap electromagnetically. This would render the dust invisible to optical telescopes designed to detect extended structures, while the gas emissions remain detectable. This elegant solution could potentially explain almost all the contradictions: a compact appearance, robust gas detection, and a complete absence of a visible tail. The significant caveat, however, is that we currently possess no known natural mechanism for an otherwise inert celestial body to generate such potent localized electromagnetic fields. This would necessitate something fundamentally active, a continuous energy generation process that defies current cometary physics. And that brings us to Hypothesis 4, the one that causes immense discomfort among many scientists, yet one that, given the profound strangeness of the observations, we're compelled to at least place on the table. What if this object is artificial? What if it is an engineered construct carrying active systems, producing the very signatures we are measuring not through geological or cometary processes, but through deliberate technological means? An artificial object could, in principle, perfectly account for all the observed contradictions. Active reflectors or modulated energy outputs could explain brightness variations. Internal energy sources could generate gas emissions without requiring the sublimation of natural ices. A compact manufactured structure would inherently appear point-like, and electromagnetic signatures, should we eventually detect them, would be expected rather than mysterious anomalies. The problem, of course, is that this constitutes an extraordinary claim, and extraordinary claims, as the scientific maxim dictates, demand extraordinary evidence, and as of now we do not possess that evidence. We have anomalies, stark contradictions, and observations that defy conventional explanation, but these are not, in themselves, definitive proof of an artificial origin. Each of these models, however speculative, makes testable predictions. The micro-outgassing hypothesis predicts that we should, with sufficient observation time and stacking, eventually detect some, albeit faint, dust production. The fragment cloud model predicts structural variations over time as the swarm dynamically evolves. The electromagnetic model predicts the discovery of magnetic field signatures, polarization anomalies, or perhaps even low-level radio emissions. The artificial model, meanwhile, predicts patterns and characteristics that do not occur naturally: precise geometric structures, spectral lines indicative of industrial processes, or temporal patterns suggesting intelligent control rather than chaotic natural phenomena. What is truly remarkable and deeply frustrating is that none of these models offer a perfect, seamless fit. Each explains certain observations while simultaneously generating new, equally challenging questions about others. The natural explanations often demand highly unlikely compositions or improbable configurations. The exotic natural explanations require the invocation of physics or phenomena not previously observed in comets. And the artificial explanation, while elegantly resolving contradictions, demands that we accept the existence of technology from an advanced non-human civilization, a leap that most scientists will, quite rightly, refuse to make without overwhelming, unimpeachable proof. But we will require one of these explanations, or something even stranger, because the standard cometary model as applied to 3i Atlas is demonstrably broken. We cannot persist in calling it a comet while it consistently refuses to behave like one. At a certain threshold, if an object persistently violates fundamental expectations, one is scientifically compelled to update the model of what the object is. We might, with Atlas, be precisely at that threshold. Part 5, formalising the challenge: what would convincingly prove non-natural? let's establish an unambiguous line in the sand. Let's meticulously define the precise evidentiary requirements needed to break the default assumption of a natural explanation, thereby compelling the scientific community to seriously consider that we are observing something engineered, something artificial. This is no longer about unrestrained speculation. This is about establishing rigorous, testable criteria that would satisfy even the most unyielding skeptical scientists. First criterion, resolve structure inconsistent with known physics. If we could acquire an image of Atlas with a resolution sharp enough to discern its intrinsic shape, and that shape revealed characteristics such as sharp edges, perfectly orthogonal angles, precise symmetric patterns, or distinct articulated components that move relative to each other, this would constitute profoundly significant evidence. Natural celestial objects formed by the stochastic processes of accretion, collisions and gravitational forces are invariably lumpy, irregular, or statistically self-similar. They do not spontaneously generate precise geometric forms. A perfectly spherical object, while striking, is not inherently suspicious. Spheres naturally minimize surface energy. However, a perfect cube, a pristine cylinder, or demonstrably articulated moving parts would demand an explanation beyond any known natural process. Second criterion, unambiguous spectral lines from compounds that don't belong. Comets, as products of primordial solar system formation, exhibit characteristic spectral signatures of water, carbon dioxide, carbon monoxide, and various organic molecules. These are precisely what we anticipate from the icy, dusty remnant. If, however, high-resolution spectroscopy were to unequivocally detect elements like technetium, an element that, on Earth, exists almost exclusively as a product of nuclear reactions, or if we observed the spectral signatures of industrial compounds, synthetic polymers, or isotope ratios that deviate dramatically from naturally occurring cosmic abundances, these would be undeniable red flags. The universe, through stellar nucleosynthesis and subsequent cosmic chemistry, synthesizes a finite palette of chemicals. Anything demonstrably outside that natural palette demands extraordinary accounting. Third criterion, multiband registration anomalies. Take images of Atlas in various distinct wavelength bands, optical, infrared, ultraviolet, X-ray, and meticulously overlay them. Natural objects display predictable patterns of emission and scattering across these bands. Hot regions will emit more infrared radiation. Dust will scatter optical light in a specific manner. Gas will emit at precise characteristic wavelengths. If the structures and features observed in different wavelength bands do not align, as fundamental physics dictates they should, if, for instance, there is a prominent structural feature visible in one band that corresponds to absolutely nothing in any other, this strongly suggests the involvement of processes far more complex than simple thermal emission and light scattering. It implies a non-natural, perhaps controlled, energy distribution or material composition. Fourth criterion, verifiable metadata and telemetry signatures. This criterion speaks directly to the unimpeachable provenance of data. If critical spacecraft observations exist, the raw image frames must be accompanied by robust, complete header information, precise timestamps, documented instrument settings, cryptographic checksums, and comprehensive calibration data. These headers must be verifiable, cross-referenceable against independent mission logs, and demonstrate an unbroken chain of custody. Inconsistencies or unexplained alterations in this metadata could indicate data tampering. More importantly, the presence of consistently verifiable, transparent metadata rigorously strengthens any claim about what was observed. You cannot credibly prove an extraordinary claim with data whose integrity or authenticity is open to question. Fifth criterion, correlated signals across different physical domains. Imagine a scenario where Atlas simultaneously exhibited an optical brightening, precisely time-locked to distinct radio bursts, concurrent X-ray flashes, and even high-energy neutrino detections. While natural astrophysical processes can indeed produce multi-wavelength emissions, e.g. blazars, pulsars, supernovae all have characteristic multi-wavelength signatures. These phenomena generally adhere to predictable patterns in known physics, something entirely novel in its multi-wavelength behaviour, particularly if the correlations are exquisitely precise and defy known natural triggers, would demand a radically new explanation. It would imply an organised, perhaps controlled release of energy across disparate physical domains. History is replete with examples where the quality and provenance of data have either made or irrevocably broken extraordinary scientific claims. The Apollo program's invaluable data tapes were almost lost to degradation and accidental overwriting, necessitating decades of painstaking restoration efforts. Astronomical archives have faced their own challenges: mislabeled data, physical degradation of storage media, and the lamentable loss of institutional knowledge when key personnel retired. The integrity and quality of the evidence are as crucial as the evidence itself. There's also the profound sociological dimension. Mission teams operate under immense pressure. Careers are often staked on successful missions, publishable results, and, crucially, avoiding claims that cannot be rigorously defended. National interests often play a role, leading to data classification or embargoes for strategic reasons unrelated to scientific merit. And the fear of professional ridicule is a powerful deterrent. No scientist wishes to be the individual who prematurely declared an extraterrestrial discovery and was subsequently proven wrong, as the professional cost is often insurmountable. So, what would an unimpeachable, credible dataset look like? It would consist of raw, uncompressed frames, not processed or cosmetically enhanced. It would include complete metadata headers that can be independently verified against multiple sources. It would contain checksums that cryptographically prove the data has not been altered since acquisition. It would be corroborated by multiple independent observations from different instruments. Crucially, it would be open access, allowing anyone to download and analyse the data and attempt to reproduce the findings. And ideally, it would have a meticulously documented chain of custody, from initial capture through storage to public release. Any video, any claim, any announcement regarding Atlas must be held to these exacting standards. If someone asserts they possess spacecraft images revealing something extraordinary, the immediate paramount questions must be: where are the raw frames? Can we independently verify the metadata? Can independent analysts access and scrutinize this data? Without this level of absolute transparency, we are merely confronted with another ambiguous observation that generates more questions than it provides answers. The burden of proof for an extraordinary claim is, quite rightly, immense. Science has progressed precisely because it is rigorous about evidence, demanding reproducibility and refusing to accept claims merely because they are exciting. But science has also advanced by taking anomalies seriously, by assiduously investigating observations that simply do not fit existing paradigms, by being willing, when data compels it, to fundamentally update its models. We are currently at a moment where the Atlas observations are sufficiently anomalous to warrant profoundly serious attention, yet not sufficiently clear or conclusive to draw definitive conclusions. What transpires next hinges entirely on whether we can gain access to decisive observations, whether new data either closes the gaps in our understanding or, more thrillingly, widens them, and whether the scientific community can expertly balance healthy, disciplined skepticism with genuine, unfettered curiosity. The framework for investigation exists. The criteria are defined. Now, we wait to see if the extraordinary evidence emerges. Part 6, ASCAP J1832, a 44-minute heartbeat in radio and X-rays. Let's momentarily pivot our attention away from Atlas and its perplexing contradictions and zoom out to a phenomenon occurring much closer to home, within our own galaxy. It's an object that is forcing astronomers to fundamentally reassess their understanding of cosmic entities. Using the Australian Square Kilometre Array Pathfinder, ASCAP, and NASA's Chandra X-ray Observatory, astronomers have unearthed a startling object designated SCAP J83320911. What makes it uniquely bizarre is its rhythmic pulse, a precise, clockwork-like heartbeat every 44 minutes, detected simultaneously in both radio waves and X-rays. No one understands why. This remarkable discovery emerged from a systematic sky survey designed to detect transient radio sources, objects that appear, disappear, or fluctuate dramatically in brightness over time. Long-period transients, or LPTs, represent a relatively nascent category of astronomical objects. They emit powerful flashes in radio wavelengths on timescales ranging from tens of minutes to several hours. They're exceedingly rare, profoundly poorly understood, and stubbornly refuse to fit into any existing classification schema for cosmic phenomena. Escape. J8332, however, elevates this enigma to an entirely new level. It is the very first such object observed to pulse in X-rays as well as radio, rendering it uniquely perplexing and scientifically unprecedented. The observational data is unequivocal and remarkably precise. The object emits a distinct 2-minute burst of radio waves, followed by an exact 42-minute period of silence, before bursting again with unerring regularity. This cycle repeats with the precision of a cosmic clock. Concurrent Chandra observations reveal X-ray pulses that are exquisitely synchronized with these radio bursts. While not perfectly overlapping in their precise temporal profiles, the correlation is undeniable and statistically robust. The object has been localized to an approximate distance of 15,000 light-years away, nestled somewhere within our vast galaxy, yet it is not associated with any obvious stellar cluster, nebula, or other known astrophysical structure. What known cosmic mechanism could possibly produce such a peculiar, rhythmic signal? The immediate suspects are typically objects characterized by intense magnetic activity. Magnetars, for instance, are a type of neutron star endowed with unfathomably powerful magnetic fields, and they are well known for their pulsating emissions. However, magnetar pulses typically occur on much shorter timescales, milliseconds to seconds, not the protracted 44 minutes observed here. This would necessitate some entirely novel configuration, some as yet unknown mechanism allowing the magnetar's field to store enormous amounts of energy slowly and then release it in such a precisely periodic fashion. No convincing model currently exists for this. Ultramagnetic white dwarfs present another possibility. These are the dense, dead cores of stars, collapsed to roughly Earth size, but still possessing remnant rotation and powerful magnetic fields. If a white dwarf was spinning with an unusually slow 44-minute period, and if it experienced active accretion or magnetic reconnection, events precisely synchronized to this rotation, periodic pulses might theoretically occur. But again, the timing is anomalous. Most white dwarfs either spin far more rapidly or have largely dissipated their magnetic fields entirely. Binary systems, two celestial objects orbiting each other, offer a third avenue of explanation. If two objects were orbiting with a 44-minute period and some form of interaction between them, such as accretion events or tidal heating, generated periodic flares, this could account for the observations. The critical hurdle here is that a 44-minute orbital period implies the objects are incredibly close, so close that they should either have already merged or be spiralling inwards rapidly due to gravitational wave emission, again presenting significant challenges to existing models. Ultimately, none of the standard astrophysical models are truly satisfying. Each requires significant parameter tweaking, the invocation of special, highly improbable conditions, or the inconvenient dismissal of certain observational facts. And this is all before we even attempt to forge a connection to 3i Atlas, which on the surface appears utterly impossible. ASCAP J9332 is a galactic object, almost certainly stellar in origin, pulsing in radio and X-rays. Atlas, conversely, is an interstellar visitor, exhibiting optical and infrared anomalies, but with no confirmed radio or X-ray detections. They represent completely disparate types of phenomena, occurring in entirely different astrophysical contexts. Yet, here is why I introduce ASCAP J9332 into this discussion. If a single object within our own galaxy can so profoundly defy all existing patterns, if it can generate a signal that does not conform to any known class of astronomical object, then we, as scientists, must cultivate a deep humility regarding our pronouncements of what is and isn't possible for other peculiar objects we encounter. ASCAP J9332 serves as compelling proof that the universe still holds untold tricks, mechanisms we have yet to catalogue, and entire classes of objects we have yet to discover. This discovery also starkly underscores the limitations of our past observational capabilities. ASCAP is a relatively new radio telescope array, operational for only a few years. Chandra, while a venerable observatory since 1999, can only observe what it is precisely pointed at. ASCAP J1832 has likely been pulsing with this extraordinary regularity for thousands, if not millions of years, and we have only just now noticed. How many other peculiar uncatalogued objects exist out there, perfectly detectable with our current technology, yet remain undiscovered simply because we haven't looked in the right place or in the right way? This question holds particular relevance for our understanding of Atlas. Prior to ASCAP J1832, one might have confidently asserted that weird periodic signals across multiple electromagnetic bands aren't a phenomenon natural objects typically exhibit. Any claim of such signals would likely be dismissed as instrumental error or misinterpretation. Now, we possess undeniable proof that such signals do exist, and, critically, we have no satisfactory explanation for them. This should compel us to be far more cautious about summarily dismissing anomalies in other objects, merely because they fail to conform to our existing and clearly incomplete models. It also suggests a potent research strategy. When confronted with one profound anomaly, one should actively search for others, seeking emergent patterns. Perhaps there is a connection, perhaps not, but we cannot know unless we actively look, which inevitably brings us to the audacious question: could Atlas and ASCAP J-32, despite their obvious differences, possibly be related by some fundamental shared physics? It sounds absurd, but to dismiss it without exploration would be unscientific. Part 7. Crosslinks. Are ASCAP J1832 and Atlas related in any plausible physics? Let us be unequivocally clear from the outset. There exists no direct established proof that ASCAP J1832 and 3I Atlas are related in any way whatsoever. They are, by all appearances, entirely distinct types of objects, operating on vastly different scales and within utterly different astrophysical contexts. What we are undertaking here is an exercise in speculative analogy, an exploration for potential shared mechanisms, an inquiry into whether the same exotic physics could, under vastly different environmental conditions, manifest in divergent regimes. Even if our ultimate conclusion is negative, the very process of meticulously thinking through such a connection illuminates what decisive tests we should be performing, what data we should be seeking. Let's begin with a comparison of energy scales. ASCAP J1832 is producing rhythmic radio and X-ray pulses. Radio emission can arise from synchrotron radiation, where charged particles spiral within magnetic fields, or from coherent plasma processes. X-rays, however, demand significantly higher energies: superheated plasma, intense magnetic reconnection events, or particle acceleration to relativistic velocities. These are inherently energetic processes, far exceeding anything we typically associate with comets, which are essentially inert mixtures of ice and rock passively heated by the sun. But what if Atlas, despite its humble appearance, is carrying or somehow generating powerful magnetic fields. Comets do possess induced magnetospheres. When the solar wind interacts with their ionized comas, a weak, transient magnetic field structure forms. This interaction is usually feeble, bearing no resemblance to the highly organized powerful fields found in magnetars or accretion systems, but its existence is undeniable. If Atlas possessed an unusually potent intrinsic magnetic field, or if it were actively carrying a significant charge or dense stream of charged particles that created substantial field structures, could those fields, under the right conditions, produce detectable radio emission? Plasma physics offers some intriguing possibilities. Coherent radio emission can arise from plasma instabilities, from regions where the density of charged particles fluctuates sharply, or from boundary layers where different plasma environments interact. If Atlas is indeed venting copious amounts of gas, that gas will inevitably become ionized by solar ultraviolet radiation. An ionized coma is, by definition, a plasma, and plasmas are capable of supporting complex waves, instabilities, and various emission mechanisms. While most of the time these emissions would be far too weak to detect, under specialized conditions, perhaps extreme charge densities or highly unusual magnetic configurations, detectable signals might theoretically be generated. However, the timing is a fundamental, seemingly intractable hurdle. ASCAP JUS 832 pulses every 44 minutes with astonishing, almost artificial regularity. Such precision strongly suggests an underlying mechanism involving rotation, stable orbital motion, or some form of deeply resonant oscillation. Atlas, in its optical observations, does not exhibit this kind of precise, minute-scale periodicity. If periodic behavior exists for Atlas, it operates on vastly different timescales, days or weeks, rather than minutes. Therefore, any shared physical mechanism would have to operate across an enormous range of characteristic times, which appears unlikely unless there is a common underlying physical principle that scales dramatically differently depending on the object's mass, size, and environment. What about X-rays? X-ray emission from comets has indeed been detected previously. This emission is produced when high-energy ions from the solar wind undergo charge exchange with neutral atoms within the cometary coma. It is typically faint, requiring exquisitely sensitive instruments to detect, but it is a real phenomenon. If Atlas possesses an unusually dense or highly active coma, then X-ray emission would not, in itself, be surprising. The crucial question, however, is whether that X-ray emission would be periodic, structured, or synchronized with any other activity we observe. Natural charge exchange is a generally uniform process, not inherently pulsed. Let us now, purely as a thought experiment, consider a unified speculative hypothesis. Suppose there exists a previously unknown class of celestial objects, whether natural or otherwise, that are characterized by the maintenance of powerful, localized magnetic fields and dense dynamic plasma environments. In a galactic context, involving stellar mass scales and compact objects, this underlying physics might manifest as ASCAP J1832, regular pulses driven by rotation or oscillation, producing both radio and X-ray emission from intense plasma processes. In an interstellar context, with a much smaller object like Atlas, this same fundamental field and plasma physics might operate but manifest differently. As a tightly confined coma, an unusual gas-to-dust ratio, and perhaps even transient radio bursts too faint or too brief to have been detected by current, uncoordinated observations. This highly speculative hypothesis generates several testable predictions. If Atlas and ASCAP J1832 genuinely share underlying physics, we should systematically search for faint radio pulses from Atlas, particularly during its perihelion passage, when its interaction with the solar wind would be strongest. We should look for X-ray flashes, precisely correlated with optical brightening or gas production events. We should seek polarization signatures in Atlas's scattered light that would indicate the presence of organised magnetic fields. Measurements of Faraday rotation, the twisting of polarization of background radio sources as their waves pass through Atlas's coma, could directly reveal magnetic field strength. Finally, neutrino detections correlated with either object would provide definitive evidence of high-energy particle acceleration mechanisms. Most of these crucial observations either have not been systematically attempted or reported. Radio telescopes have not to date been tasked with systematically monitoring Atlas at high-time resolution. X-ray observatories might not have been pointed at it during its most active phases. The decisive data required to either confirm or definitively rule out such a speculative connection might simply not exist yet. However, the comparison itself is invaluable, even if the ultimate answer proves to be negative. If we meticulously observe Atlas at radio wavelengths during its next active period and detect no coherent plasma emission, no synchrotron radiation, no radio-producing mechanism whatsoever, that result significantly constrains our models. It eliminates an entire category of hypotheses. Conversely, if we do find radio pulses, or X-ray correlations, or any of the electromagnetic signatures we are predicting, that would be extraordinary. It would suggest that Atlas is engaged in phenomena far outside the normal behaviour of comets, phenomena that connect it to active stellar objects like ASCAP J1932. Such a discovery would firmly propel us into exotic territory where conventional explanations cease to hold, forcing us to seriously entertain alternatives we might otherwise prefer not to contemplate. The scientific imperative is to be systematic. Anomalies observed in one object can inform how we conceptualize and investigate anomalies in another. Patterns often emerge when comparisons are made across seemingly disparate phenomena, and sometimes the wildest, most far-fetched seeming connections turn out to possess an underlying truth, because nature often reuses the same fundamental physics in vastly different contexts. We will not know until we look. Part 8. The 220 PeV ghost particle. Why a single neutrino matters. A single particle, almost imperceptible, yet carrying an unimaginable payload of energy, irrevocably changed everything. On a day that should have passed without remark, deep beneath the churning surface of the Mediterranean Sea, an intricate array of detectors known as KM3net registered an event that, according to our established and comfortable understanding of cosmic ray physics, should not, by all rights, exist. A neutrino, an elusive ghost particle, possessing an energy of 220 peta-electron volts, PV, slammed through the detector. Its passage left a fleeting, ethereal trail of Cherenkov light, a luminous echo in the abyss that told a story of the most violent, cataclysmic processes imaginable in the universe. Let me contextualize what that number truly signifies, because at this scale, figures lose their intuitive weight. A peta-electron volt is 1,000,000 billion electron volts, an almost incomprehensible quantity of energy. To put this in human-scale terms, the protons accelerated within the Large Hadron Collider, the most powerful particle accelerator ever constructed by humanity, achieve energies of approximately 14 tera-electron volts, TeV. This single neutrino carried 16,000 times more energy than those maximally accelerated protons. It was, in essence, a cosmic bullet, fired by an accelerator so unimaginably powerful, so fundamentally extreme, that we currently lack a complete theoretical framework to explain its operation. Neutrinos are, by their very nature, ghost particles. They interact so weakly with normal matter that they can traverse vast cosmic distances, including entire planets, as if matter simply isn't there. As you read this, billions of neutrinos, originating from the sun's core, are streaming through your body, through the Earth's mantle, and continuing unimpeded into the vacuum of space, without encountering or interacting with a single atom. They possess almost no mass, no electric charge, and none of the properties that would allow them to meaningfully bump into ordinary matter. detecting these elusive particles therefore demands enormous volumes of transparent material, either glacial ice or deep seawater, meticulously instrumented with arrays of ultra-sensitive light sensors. These sensors vigilantly watch for the exceptionally rare occasions when a neutrino does interact, producing a secondary charged particle that emits a flash of Cherenkov radiation as it travels faster than light can in that particular medium. The KM3-NET collaboration operates in the depths of the Mediterranean, utilising the sea itself as its vast detector volume. Arrays of optical sensors suspended on towering cables continuously monitor cubic kilometres of seawater for the telltale flash of Cherenkov light that signals a neutrino interaction. The ARCA component of KM3-NET detected this particular event, meticulously recording the characteristic pattern of a muon track. Scientists then painstakingly worked backward through the complex physics to definitively determine that the parent neutrino must have possessed an astonishing energy of at least 220 PeV. The analysis has been rigorously confirmed. This is unequivocally not a glitch, not a misidentification, but a real, verifiable event. Why does this singular detection matter so profoundly? Because neutrinos at these extreme energies are irrefutable messengers from cosmic accelerators operating at scales we barely comprehend. The most powerful candidates for these accelerators are typically blazars, supermassive black holes residing at the centres of distant galaxies, actively feeding on surrounding matter and launching colossal, relativistic jets of plasma at nearly the speed of light. Within these jets, protons can be accelerated to immense energies. When these high-energy protons collide with ambient photons or matter, they produce ephemeral particles called pions, which subsequently decay into high-energy neutrinos. Gamma-ray bursts, the brief, intense death screams of massive stars collapsing into black holes, represent another potential source. Any phenomenon capable of accelerating particles to these truly extreme energies is, by definition, operating at the very limits of known physics. Now here is the speculative, yet intellectually compelling connection to Atlas. It is tenuous, certainly, but worth exploring. Could 3i Atlas be embedded within, passing through, or somehow intimately connected to a high-energy astrophysical environment? This object originated from interstellar space. We have a rough understanding of its trajectory, allowing us to trace its path back into the galaxy. But we possess virtually no knowledge of the specific environments it encountered during its millennia-long journey. Did it pass through a supernova remnant, skirt the edge of a pulsar wind nebula, or traverse regions of space where intense magnetic fields or extreme plasma densities create powerful particle acceleration zones? The speculation can extend even further. If Atlas is carrying exotic matter, if it possesses magnetic fields that we do not yet comprehend, or if it has inherent properties we have yet to detect, could it interact with the solar wind or the interplanetary medium in ways that generate high-energy particles? Could it, through mechanisms entirely distinct from those operating in normal comets, seed the production of neutrinos? This line of reasoning sounds absurd, perhaps even outlandish, until one remembers the foundational uncertainty. We do not, in fact, know what Atlas is. We classify it as a comet because it is within our solar system and exhibits some volatile activity, but everything about it is anomalous, contradictory, and stubbornly defies easy categorization. A concrete, testable strategy exists. Neutrino detectors such as KM3-NET, IceCube at the South Pole, and other global facilities maintain continuous real-time monitoring. Their data is meticulously time-stamped and direction resolved. If a burst of high-energy neutrinos were to occur, precisely coincident with Atlas's perihelion passage, or with its documented active phases, or with any other unusual behaviour observed optically or spectroscopically, such a correlation would be profoundly significant. The probability of such a coincidence occurring purely by chance is calculable, and, for a statistically robust correlation exceedingly low. A sufficiently strong correlation would be compelling evidence of direct physical connection. This approach has yielded scientific breakthroughs before with other astrophysical phenomena. When IceCube detected neutrinos originating from the direction of a known blazar during an active flaring phase, it provided definitive confirmation that blazars are indeed powerful neutrino sources. The nascent field of multi-messenger astronomy relies precisely on correlating signals across different types of particles and radiation: light, neutrinos, gravitational waves. Each messenger offers a unique window into the source, because each is produced by distinct physical processes and travels through space in different ways. Neutrinos are uniquely special messengers precisely because they are so difficult to stop. If Atlas were producing them, they would escape directly and unimpeded, carrying pristine information about whatever PROS is generating them. Gamma rays might be absorbed by intervening dust or gas. Radio waves might be scattered or refracted. But neutrinos punch through everything, arriving at Earth carrying an undeniable directional signature back toward their source. They are the ultimate cosmic messenger for probing environments that are otherwise utterly opaque. The 2x20 PeVy neutrino detection is irrefutable proof that such messengers exist, that we inhabit a universe populated by processes so violent and so powerful that they can produce particles of such unimaginable energy. It serves as a stark reminder that our existing census of cosmic phenomena is far from complete. We do not yet comprehend all the ways nature can accelerate particles, generate fields, or produce high-energy radiation. New classes of objects, new mechanisms, are still actively being discovered. So, when we scrutinize Atlas, with its cascade of contradictions and anomalies, we should hold in mind that the universe has already demonstrated its capacity to surprise us with phenomena we did not predict. ASCAP J32 pulses in ways no model fully explains. A neutrino of previously unimaginable energy arrived from somewhere. Black holes merge and produce gravitational waves, a phenomenon we only learned to detect a mere decade ago. The inventory of cosmic weirdness continues to expand. Perhaps Atlas is simply a comet with an unusually exotic composition, and we are merely overthinking it. But perhaps it represents another unprecedented entry in the growing catalogue of things we did not expect. Another phenomenon that will necessitate either entirely new physics or entirely new categories of explanation. The only rigorous way to determine this is to maintain diligent observation, to continuously seek correlations, and to persistently question whether seemingly disparate anomalies might, in fact, be profoundly connected. And to accomplish that effectively, we require unfettered access to all available data, including those crucial observations that might lie dormant in archives, patiently awaiting analysis. Part 9, Space Weather Overlay, for CMEs, aurora forecasts and why environment matters. While our gaze has been fixed on distant enigmas and exotic particles, something closer has complicated everything. The Sun has turned unruly. 4 powerful coronal mass ejections, CMEs, blasted off in quick succession, all Earth-directed, with arrivals forecast for October 15-17, 2025. Each billion-ton cloud of magnetized plasma races at millions of kilometers per hour. When it slams into Earth's magnetic field, geomagnetic storms ignite. For aurora chasers, that's thrilling. Storms funnel charged particles into the upper atmosphere near the poles, where collisions with atmospheric gases paint the sky with shimmering curtains of light. Stronger storms push aurorae to mid-latitudes, making rare, spectacular shows likely from this CME train. For astronomers chasing faint, ambiguous targets like 3i Atlas, space weather is a menace. The same particles that power aurorae inject noise into delicate measurements. Radio work suffers from ionospheric scintillation, rapid, frequency-dependent flickering far worse than optical twinkling. Cosmic ray showers spike detectors with bogus events. optical data picks up extra air glow, a diffuse background from excited molecules that quietly buries signal. Spacecraft fare no better. Solar energetic particles flip bits in electronics, corrupting data or mimicking detections. Star trackers can be peppered by high-energy hits, inventing stars and confusing attitude control. Imaging sensors show noise spikes, hot pixels, and bright streaks from particle strikes. Post-processing can filter some of this, but never perfectly. Here's the insidious part. Space weather offers ready-made alibis. Missing frames? A CME hit the window. Strange artifacts? Solar particles? Telemetry gaps? Safe mode during the storm? All are real phenomena, and awfully convenient excuses. So how do we separate unavoidable solar impacts from more troubling causes of missing or compromised data? By following the signatures, cosmic ray hits appear as sharp, isolated pixel spikes. Scintillation has characteristic timescales and frequency behaviour. Safe mode entries leave distinct telemetry and log patterns. With full granular metadata, engineering logs, instrument diagnostics, and bracketing calibration frames, we can usually reconstruct precisely what happened and why. The profound problem arises when such comprehensive access is denied. If one is merely informed that data was lost due to space weather, without the accompanying detailed logs, the instrument diagnostics, and the crucial calibration frames, then the claim cannot be independently verified. It might be true, it might be a convenient simplification of a more complex problem, or it might be deliberately obscuring something else entirely. This is not paranoia. This is the fundamental principle of data integrity in scientific research. Scientific claims demand verifiable evidence, and evidence in turn demands impeccable provenance. You need to know precisely where data originated, how it was processed, and what transpired with it at every stage of its journey. When gaps appear in that chain of custody, when explanations are vague or incomplete, the data's reliability for making robust scientific claims, whether those claims are mundane or utterly extraordinary, is severely compromised. Historical examples abound. The Hubble Space Telescope's NICMOS instrument suffered a cooling system failure that was initially attributed to generic thermal issues, but later turned out to involve specific, complex mechanical problems that took years to fully diagnose. The Mars Observer spacecraft was tragically lost during orbital insertion, with telemetry suggesting a fuel line rupture, yet the incomplete nature of the data left ample room for alternative theories and lingering ambiguity. When data is incomplete, explanations inevitably remain ambiguous. For Atlas observations, this environmental factor is particularly critical because we are relying on a patchwork of instruments, each with its own specific vulnerabilities to environmental effects. Ground telescopes contend with atmospheric turbulence and terrestrial weather. Space telescopes grapple with relentless radiation and thermal cycles. Radio arrays must cope with highly variable ionospheric conditions. If all these instruments are yielding slightly divergent results, how much of that divergence is attributable to genuine physical differences in what they are observing versus the cumulative impact of instrumental and environmental effects? The 4 CMEs arriving this week will only compound this complexity. Any observations conducted during this window will necessitate accounting for significantly enhanced background noise, potential instrumental anomalies, and increased calibration uncertainty. This doesn't render the observations worthless, but it undeniably widens the error bars, and larger error bars directly translate to greater ambiguity regarding Atlas's true nature. There's also a nagging timing question that warrants consideration. If truly decisive spacecraft observations of Atlas do exist, frames that would definitively resolve the profound contradictions we've been discussing, why have they not been released, especially during a week when severe space weather provides a ready-made, perfectly credible explanation for any potential delays or data issues? It would be the opportune moment to state, we intended an earlier release, but the CMEs complicated our data processing. Here is the validated data we now possess. The conspicuous absence of such an announcement is noteworthy, though not necessarily indicative of malfeasance. Space weather, in this context, embodies a form of structural blindness that we face when attempting to understand cosmic phenomena, the complex dynamic environment between us and the object, between the instrument and the data archive, between the moment of observation and the eventual publication, inevitably introduces noise, gaps, and uncertainties. Some of this is unavoidable physics, some is attributable to technological limitations, and some, perhaps, is due to institutional or procedural bottlenecks, the specific ways data is handled and released by organisations with their own distinct priorities and constraints. To pierce through this structural blindness, we require redundancy, multiple instruments, employing diverse observing strategies, and multiple independent analyses of the same dataset. We need absolute transparency regarding what is being observed, when, what data quality flags are being applied, and how processing pipelines are configured. And critically, we need to foster a scientific culture where asking probing questions about data provenance is not perceived as adversarial, but as an absolutely essential component of conducting rigorous, credible science. Part 10: Instruments, Biases and the Archive. How we're structurally blind. Let's trace the hidden life of astronomical data, from the instant a photon touches a detector to the moment a researcher can finally access it. This quiet journey, though technical and unseen, defines the boundary between what we can know and what remains forever invisible. It begins with the detector. A photon lands, becomes an electrical signal, then a digital number. But every conversion loses something, through electronic noise, quantization errors, or uneven detector sensitivity. Cosmic rays strike, leaving false signals. Hot pixels and column defects introduce patterns that mimic real phenomena. Before the data even leaves the instrument, it is already a mixture of truth and artifact. Next comes compression. Spacecraft generate mountains of data but possess meager bandwidth. Images must be squeezed, sometimes losslessly, often not. Lossy compression discards less important details, yet what's dismissed might one day prove vital. Every bit saved can be a clue erased. Then the ring buffer problem. Spacecraft memory is finite. Data is stored temporarily, waiting for a communication window to Earth. If transmission fails, or if higher priority files overwrite the buffer, those lost frames vanish forever, overwritten by silence. Even transmission is a competition. Deep space network time is scarce, and missions queue for minutes of contact. Engineering telemetry takes precedence, then primary science, then secondary targets. Observations of something like 3i Atlas could easily sit idle for weeks, trapped behind higher-ranked priorities. Once received on Earth, data enters another labyrinth. Raw frames are reformatted, metadata attached, coordinates, exposure time, filter, quality flags. A mislabeled header, even by a fraction, effectively buries the data. Archives migrate, software evolves, and with each migration come risks. Broken links, checksum mismatches, corrupted files. Among millions of entries, some inevitably go dark, unseen not because they were hidden, but because they were misplaced. Finally, institutional barriers, proprietary periods and embargoes grant mission teams exclusive access for months or years, ensuring they publish first. It's a fair policy, but it means some of the most significant discoveries may lie dormant in private archives. Add bureaucratic inertia, understaffed teams, delayed releases, incomplete documentation, and vital observations can remain locked away indefinitely. From photon to public archive, the path of knowledge is fragile. Every stage is a potential point of loss, not through conspiracy, but through complexity. Understanding where truth can vanish is the first step toward ensuring it is never lost again. history keeps ambushing us with rediscoveries. Reanalyses of Hubble archives have revealed objects missed the first time. Lost Voyager tapes resurface decades later. Amateurs routinely find comets and asteroids in public images professionals overlooked. The archives are simply too vast for any single pipeline or team to exhaust. Call it structural blindness. We only see the sliver of the universe that survives every gate. Successful observation, downlink, labeling, archiving, an analysis by someone with time, tools, and curiosity. Everything else remains latent, present, but effectively invisible. For 3i Atlas, this matters. Apparent contradictions between instruments may be artifacts of pipelines, not physics. TESS excels at stellar photometry. A diffuse coma can be algorithmically invisible. Grand reductions often assume point sources, suppressing faint tails. JWST's spectrographs are exquisitely sensitive to molecules, yet not optimized for wide-field dust morphology. Every instrument and its software bakes in bias. The missing Psyche frames may have mundane explanations: bandwidth triage, downlink delays, mislabeling, reprocessing, or low priority queues. None require conspiracy, but absence without clarity breeds frustration. If images exist, they must be auditable. If they don't, we need a post-mortem on why windows were missed. Transparency is as valuable as the data, so the research strategy is obvious. Don't wait for polished releases, mine the raw, pull frames and reprocess with coma-friendly assumptions, use difference imaging and motion filters, hunt for metadata anomalies, cross-check logs against what's actually in the vaults, escalate with formal access requests and foyers. Citizen science is pivotal. Unconstrained by institutional incentives, amateurs and data scientists can ask impolite questions, share code, and iterate quickly. Astronomy's record is full of their wins, and the digital era multiplies their reach. Structural blindness is real, not terminal. Overcoming it demands persistence, specialized skill, coalitions, and steady pressure on institutions to fix pipelines, accelerate releases, build, and open the books. The photons already hit the detectors. Bits exist somewhere. The question is not whether the universe spoke. It did. The question is whether we will retrieve, verify, and share what it said. That's policy and priority as much as physics. Part 11. The data hunt. Specific, immediate forensic actions to perform. We can no longer wait for answers to drift from speculation into certainty. The time for theory is over. The time for method has arrived. What follows is a precise forensic roadmap to uncover whether Psyche ever saw 3i Atlas, and if so, what it captured. Step 1. Define the observation windows. Begin by calculating the exact moments when Atlas could have entered Psyche's field of view. Using JPL's Horizons database, we can retrieve the real-time ephemerides for both bodies, accounting for orbital geometry and solar angles. These calculations reveal when Psyche's cameras could safely point toward Atlas without risking solar glare or operational limits. Every factor matters: spacecraft orientation, sun angle, and camera protection constraints. Within those narrow windows may lie a handful of frames that quietly contain the object in question. Step 2. Know the instruments. Psyche's cameras are thoroughly documented in NASA's technical archives, their pixel scale, field of view, and limiting magnitude all public. By estimating Atlas's brightness at each potential window, we can test feasibility. Was it bright enough to register, or too faint to detect? A small cometary outburst, a change in phase angle, or an extended coma might have made it visible even in calibration frames. Establishing this detection threshold distinguishes the merely possible from the genuinely observable. Step 3. Search the archives. The Planetary Data System, PDS, holds every image, calibration frame, and engineering shot from Psyche. Its structure is labyrinthine but searchable. query by date, instrument, and sky coordinates using automated scripts. Python tools like Astrobiology can parse the metadata and flag any frames intersecting Atlas's predicted position. Don't stop at science images. Hidden data often lives in engineering or rejected directories. Many groundbreaking discoveries have emerged from data once dismissed as noise. Step 4. Request the missing data. If the public archives yield nothing, precision turns into persistence. File Formal Freedom of Information Act (FOIA) requests for all raw frames taken during the identified intervals. Be exact. List timestamps, instrument modes, and desired metadata. Even a refusal, citing national security, proprietary review, or incomplete processing, is a clue. The response itself tells us whether the data exists, where it is held, and why it remains unseen. International collaboration may extend this process to ESA or JAXA, whose participation could illuminate data otherwise beyond reach. Step 5. Verify with mission logs. Every spacecraft keeps a diary, attitude data, power records, and transmission logs. These files reveal where Psyche was pointing, when cameras were active, and what was sent back to Earth. If the logs confirm imaging activity at Atlas's coordinates but the PDS shows nothing, the gap becomes the story. Missing data could mean transmission loss, corruption, or deliberate exclusion, each with distinct implications. Through these 5 coordinated steps: calculation, instrumentation, search, request, verification, the truth can be extracted from noise. Whether Atlas turns out to be an ordinary interstellar visitor or something far stranger, the answer already exists within the data. What remains is not speculation, but resolve. The discipline to look, to question, and to uncover what the universe has quietly recorded. 6th, inspect data integrity. Every digital file carries a fingerprint, its checksum, a cryptographic signature ensuring authenticity. Archives worth trusting maintain these hashes and full version histories that record when files were added or modified. Request these records. Search for anomalies, gaps, unexplained reprocessing, or late modifications. Such patterns reveal whether data was lost, altered, or quietly replaced. Compare checksums across mirrored archives to confirm synchronization and verify whether changes align with official mission logs. A transparent version history distinguishes honest recalibration from quiet redaction. 7th, reprocess what's public. Even if no Atlas file is labeled, raw Psyche images from the relevant periods remain a goldmine. Download them. Modern algorithms can extract what automated pipelines missed. Stack the frames, subtract star fields, train neural networks to find faint moving sources. Machine learning can flag subtle anomalies human eyes might miss, but humans, in turn, must verify what the code rejects. Some detections might appear as noise, artifacts, or cosmic ray hits, yet within those dismissed pixels could lie Atlas, unnoticed in plain sight. 8th, build a citizen audit. This search is too vast for one person. Form a distributed coalition. Amateur astronomers, data scientists, programmers, legal experts versed in FOIA, and researchers willing to share tools and insight. Collaborate openly on GitHub, coordinate in real time on Slack or Discord, and enforce rigorous documentation so every finding can be verified. History has shown what citizen science can achieve, from mapping galaxies to discovering exoplanets. Collective scrutiny is a force multiplier. One mind can miss what 100 curious ones cannot. 9th, secure whistleblower channels. If the data exists but remains suppressed, insiders may hold the key. Establish encrypted anonymous channels for verified disclosures, protected by cryptography and strict operational discipline. Be skeptical. Disinformation thrives in anonymity. Cross-check every claim against facts. Extraordinary assertions demand extraordinary proof. but authentic leaks have reshaped science before. They can again. 10th, combine forensics with public pressure. Data archaeology is slow, but public attention accelerates it. Write to observatory directors, mission leads, and funding agencies. Petition for open access and faster data releases. Public engagement transforms priorities. When enough people care, institutions respond. Mobilize journalists and science communicators to translate this quest into a story. The search for hidden images of an interstellar visitor. Curiosity, amplified, becomes influence. The larger purpose? This will not be quick. It demands precision, collaboration, and relentless patience. Yet every step, integrity checks, reprocessing, auditing, advocacy, is concrete and achievable with existing tools. The potential reward is profound, a glimpse of Atlas itself, revealing whether it is natural, anomalous, or something entirely new. Even failure is informative. If no data exist, we learn how opportunities slip through institutional cracks and how to prevent that next time. Science advances not only through discovery, but through the discipline of searching, even when the answer is absence. The hunt begins now. The instruments exist. The methods are proven. What remains is collective will, the courage to look deeper, and the patience to turn speculation into knowledge. Because truth rarely waits to be handed down, it waits to be uncovered. Part 12. Experimental tests. What new observations would kill or confirm alternate models? Even if the long-sought Psyche images never surface, we are not powerless. There remains a clear, rigorous scientific path to uncover the truth of 3i Atlas, a series of focused, decisive tests capable of distinguishing between natural and exotic possibilities. Test 1. High-resolution polarimetry at multiple phase angles. Polarimetry measures how light is polarized when scattered by a surface or particles, revealing crucial information about composition and texture. Different materials, dust, metal, ice, produce distinct polarization patterns. By observing Atlas across a range of phase angles, the geometric relationship between the Sun, the object, and Earth, we can decode its surface properties. A match to typical cometary dust would support a natural origin, but a polarization curve resembling metallic or engineered surfaces would be profoundly anomalous, suggesting artificial or structured material. The technology already exists on large telescopes and space observatories. What's needed is careful calibration and sustained observation. Test 2. Narrowband imaging. During dormant phases, most observations are focused near perihelion, when Atlas is brightest and most active. Yet its true nature may reveal itself in its quieter phases, when it drifts far from the Sun. Using narrowband molecular filters to isolate emissions of carbon monoxide, carbon dioxide, or water would show whether activity fades as expected. In normal comets, emission drops sharply beyond 3 AU, with near silence past 5 AU. If Atlas continues producing gas far from solar heat, something else, an exotic chemistry or internal energy source, must be driving it. Tracking its full orbit, from active to dormant phases, would map this relationship precisely and expose any energy anomalies. Test 3. Deep stacking and adaptive optics. Imaging. High-resolution imaging achieved by stacking hundreds of exposures and correcting for atmospheric distortion through adaptive optics could unveil subtle structures invisible in single frames. Space telescopes like JWST or Hubble would provide even greater clarity. A truly natural object should show irregularities, jets, fans, or uneven albedo patterns. But perfect symmetry or geometric edges would be deeply suspicious, hinting at deliberate design. Observations at multiple wavelengths could separate dust from gas, producing colour maps that trace composition and motion. Each test is feasible with current technology. Together, they form a disciplined strategy. Probe surface composition, track out gassing patterns, and scrutinise physical structure. Whether Atlas proves to be natural, exotic, or something else entirely, the data will sharpen our understanding of how matter behaves beyond the solar norm, and perhaps how intelligence manifests across the stars. Test 4. Coordinated multi-wavelength monitoring. Imagine an orchestra of telescopes, radio arrays, X-ray satellites, and optical observatories on Earth and in orbit, all focused simultaneously on Atlas during an active phase. The goal, to catch the cosmos in the act of coordination. If optical brightening aligns perfectly with radio pulses, that's evidence of electromagnetic processes beyond ordinary thermal radiation. If X-ray flashes coincide with gas jets, it points to plasma dynamics producing high-energy photons. But if every wavelength behaves independently, optical, radio, X-ray, each dancing to its own rhythm, that would favour the natural chaotic behaviour of ordinary comets. Synchronised variations across unrelated wavelengths, though, would be astonishing, suggesting a shared trigger, or perhaps deliberate control of energy release. To see it, we must maintain relentless monitoring. Some processes unfold in seconds, others over days. Capturing both requires constant global observation, from quick bursts to long-term patterns. Test 5. Neutrino and cosmic ray coincidence. Next, a more audacious search for subatomic whispers. Neutrinos, ghostly particles passing through Earth by the trillions, are almost impossible to detect. Yet detectors like IceCube in Antarctica and KM3Net in the Mediterranean can record the rare few that collide. If any neutrino event occurs exactly when Atlas flares, the odds of coincidence are vanishingly small. Such a detection would transform Atlas from a curious comet into a source of high-energy astrophysics. Natural comets do not emit neutrinos or cosmic rays. If this one does, it's rewriting the rulebook. We can also consult cosmic ray observatories like the Pierre Auger array for spikes during Atlas activity. Even null results refine our limits. The cost is minimal, the potential discovery monumental. Test 6. Rotation and light curve analysis. Every comet spins, its brightness rising and falling as its surface turns toward the sun. Careful analysis of this light curve can reveal shape, rotation period, and internal structure. If Atlas's brightness varies regularly, we can infer its geometry. Irregular fluctuations suggest rugged topography. Smooth curves imply a spherical or uniformly bright surface. But if the light curve is too perfect, lacking the tiny irregularities every natural object shows, that would raise eyebrows. A flawless rhythm could mean either an improbably featureless body or active stabilization, an entity adjusting itself. If gas emissions pulse at exact rotation phases or brightness shifts lead solar heating, it would hint at controlled modulation rather than passive response. Automated photometric networks can monitor Atlas around the clock, building a precise rotational fingerprint that reveals whether we're observing nature's randomness or something far more deliberate. Test 7. Magnetic field detection via Faraday rotation radio waves passing through magnetized plasma twist. A phenomenon called Faraday rotation. Measuring this twist tells us about the magnetic field strength of the intervening medium. If Atlas carries its own magnetic field, background radio sources glimpsed through its coma should show measurable rotation. Achieving this requires exquisite geometry, Atlas crossing in front of a bright radio beacon, and ultra-precise polarization measurements. Comets are not magnetic. Their small, icy, non-metallic nuclei cannot sustain dynamos. Detecting an intrinsic field would therefore be extraordinary, hinting at metallic composition or engineered electromagnetic systems. VLBI radio arrays can measure such polarization shifts to within fractions of a degree. Should any appear, it would redefine what a comet can be. The synthesis. Each of these tests isolates a piece of truth. If Atlas behaves like a natural comet, we'll see thermal emission tied to sunlight, irregular light curves, no neutrinos, no magnetic field, and chaotic, uncorrelated activity. If it's merely a fragment swarm, we'll detect incoherent light variations and scattered polarization, but no organized signals. If it's a naturally exotic, electromagnetically active object, we might find partial correlations, magnetic traces, and anomalous emissions even far from the Sun. And if it's artificial, then the signatures will defy randomness entirely. Geometric precision, spectral anomalies, synchronized behavior, perhaps even temporal patterns suggesting control. That is the essence of science. Predictions before observations. We lay out clear, falsifiable outcomes so that evidence, not imagination, decides. What must end are ambiguous findings, data that let everyone see what they already believed. The path forward demands courage from the astronomical community, coordination across observatories, precious telescope time, and a willingness to pursue what might seem an improbable chase. But the stakes justify the effort. Either we confirm Atlas as a uniquely volatile comet, expanding our understanding of solar system chemistry, or we discover it represents something unprecedented, forcing us to rewrite our conception of what can exist in interstellar space. The observation windows are coming. The universe has offered us a question of staggering importance. The only remaining mystery is whether we will have the discipline and the curiosity to answer it. Part 13. If it were artificial, consequences for SETI policy and scientific procedure. Let's face the implications head on. If, even hypothetically, 3i Atlas is not natural, everything shifts. Our SETI framework, our discovery policies, and our standards for validating extraordinary claims all require rapid, radical revision. Rethinking SETI. Classic SETI hunts deliberate radio beacons from distant planets. But if technological artifacts can traverse interstellar space and show up in our own backyard, the search space changes. An artifact need not broadcast. It could be dormant, passively observing, or communicating in ways we don't recognize. Detection would hinge on anomalous physical behavior, properties incompatible with known natural processes, rather than decoded messages. SETI would pivot from radio toward wide optical surveys, high-resolution spectroscopy, precision astrometry, and any method suited to isolating outlier objects among millions of natural bodies, raising and reframing the bar. Traditional SETI sets a punishingly high threshold to avoid false positives. With inspectable artifacts, the burden of proof evolves. We can pursue multiple independent lines of evidence and tests impossible for a lone signal. The operative question becomes, does this object's multimodal behaviour fit an artificial model better than any plausible natural one? Policy and governance gaps. Who owns the data and the decision if non-human technology is confirmed? Space agencies, national security bodies and international organisations, e.g. UNCOPIOS, would inevitably contest authority. No binding, universally accepted legal framework exists. Disclosure and data integrity. The IAA SETI principles are voluntary and radiocentric, not tailored to in-solar system artifacts. To withstand rightful skepticism, claims must rest on an unimpeachable chain of custody. Raw frames with cryptographic signatures, independent corroboration, open archives enabling full reproduction, and transparent processing logs. Anything less invites accusations of error, fraud, or misinterpretation, and collapses credibility. International coordination would be essential, but nearly impossible. Nations have different priorities, varying transparency, and complex ties between their space and military institutions. A detected artifact could be treated as a strategic asset, not shared science. Balancing openness with security would demand delicate diplomacy at the highest level. History offers few precedents. The discovery of pulsars or the mysterious WOW signal provoked brief speculation about extraterrestrial origins, but never required a global response. the discovery of DNA or nuclear fission reshaped civilization, yet even those pale beside the implications of confirming non-human technology. Ethical dilemmas would multiply. Who owns such an artifact, its finder, humanity, or its creator? Do we have the right to study or even touch it? What if it's observing us or reacts unpredictably to interference? Science fiction has asked these questions for decades. Reality would not wait for neat answers. Equally dangerous is how to handle revelation. Announcing prematurely risks destroying scientific credibility for generations. Concealing proof would be equally irresponsible. Striking balance between caution and disclosure would test judgment beyond precedent. The public reaction would be volatile. Excitement, fear, denial, conspiracy. Managing truth responsibly, without panic or propaganda, might prove harder than the discovery itself. Our institutions are not ready, scientifically, politically, or culturally, yet that must not stop inquiry. It should compel us to prepare now. We must establish protocols before the extraordinary becomes real. The scientific process, observe, hypothesize, test, revise, still applies, though under far greater scrutiny. Extraordinary claims will require extraordinary evidence, transparent data, open verification, and integrity beyond reproach. If Atlas is artificial, persistent observation will expose its signatures, structure, composition, and motion that no natural object could mimic. And if it is not, disproving it will be equally valuable. Either outcome deepens our understanding of the cosmos and forces us to refine how we recognize intelligence itself. The search, not the answer, is what truly advances science. Part 14. Broader cosmic patterns. Are we in a new era of cosmic weirdness? Let's step back and look at the larger cosmic picture. We have 3i Atlas, a visitor that behaves like no known comet. ASCAP, J1932, pulsing every 44 minutes with eerie precision, defies classification. And a 220 peta-electron volt neutrino, a particle from a cosmic accelerator so powerful we can scarcely imagine it. Are these isolated curiosities, or signals that the universe is far stranger and more intricate than we once believed? In just a decade, our tools have transformed. Wide-field surveys like Zwicky, Pan-STARRS, and soon Vera Rubin scan the sky endlessly, catching what flickers or moves. Radio arrays such as ASCAP and MeerKAT expose transient bursts invisible to older generations. Neutrino detectors now map the cosmos through ghostly particles, and gravitational wave observatories listen to space-time itself. Each advance reveals phenomena that once hid beyond reach. Think of fast radio bursts, unknown until 2007, now detected daily, still mysterious. Or the first neutron-star merger witnessed in 2017, confirming predictions once confined to theory. The more we look, the more surprises emerge, because we're finally sensing the universe through many eyes and ears at once. Artificial intelligence accelerates this revolution. Machine learning scans millions of spectra and images, spotting patterns and anomalies humans might never see. Yet this abundance of discovery brings a paradox. More data means more noise. Huge datasets guarantee false alarms, statistical flukes masquerading as miracles. In a billion measurements, 1 in a million events appear by the thousands. So how do we separate genuine new physics from illusion? Through correlation and replication, real phenomena reappear. They cluster by type, by place, by time. False ones vanish when re-examined. Atlas is strange, but only one object. ASCAP J1832 is strange, but only one. The 220 PeV neutrino, a single flash. Are they connected? Or are we seeing constellations where none exist? Across astronomy, this cosmic weirdness keeps widening. Some exoplanets possess atmospheres that shouldn't persist, or orbits that models can't explain. Tabby's star once sparked talk of alien megastructures before dust proved the culprit. Entire galaxies have been found either nearly devoid of dark matter or saturated with it, confounding our theories of formation. AI now aids nearly every field, from identifying gravitational lenses to predicting stellar evolution, yet its strength is also its blindness. It finds only what it's trained to see. Anything truly unprecedented risks being dismissed as error. We stand then at a peculiar frontier, armed with instruments capable of perceiving the unimaginable, yet uncertain whether we'll recognise it when it appears. The universe keeps whispering its strangeness. The question is whether we're listening clearly enough to hear what it's really saying. At the heart of all this lies a deeper question. Are we uncovering true cosmic strangeness, or simply creating it through our own biases, instruments, and limited imagination? Has the universe always been this strange, only now revealed by sharper eyes? Or is strangeness just what we call the frontier of our ignorance, soon to be explained once our theories catch up? I lean toward the first view. The universe owes us no familiarity. Quantum mechanics is strange. Relativity is strange. Dark matter and dark energy are stranger still. Every great leap in science has shown that reality operates on principles that first seem absurd, until a new framework makes them comprehensible, yet never less astonishing. Perhaps this truly is a strangeness era, when our tools and minds have finally evolved enough to glimpse the universe as it really is. Extreme, elegant, and endlessly unpredictable. Atlas, ASCAP, J18-2, and those high-energy neutrinos may be the opening notes of a vast, unseen symphony of cosmic oddities, or mere noise mistaken for melody. The only way to know is to keep watching, testing, and measuring without mercy or prejudice. Science advances by daring to question the impossible and proving it wrong, or right, with evidence. More interstellar visitors are coming. Oumuamua and Atlas were only the first. The upcoming Vera Rubin Observatory will likely find hundreds more, each a messenger from another star, carrying truths we have yet to imagine. The strangeness is not ending, it's only beginning. And that, far from frightening, is the most exhilarating truth of all. Part 15, Final Synthesis, what we actually know, what we should demand, and the 3 tests that will settle this. Let's bring this cosmic puzzle back down to Earth and focus on what we truly know, what remains uncertain, and what will still be tested. What we know for certain, the TESS satellite collected over 9,000 frames of 3i Atlas and found no extended coma, only a point of light, a result that has been independently verified. The James Webb Space Telescope and other infrared observatories confirm the presence of gas, carbon dioxide and water vapour, indicating real volatile activity. Meanwhile, ground-based optical telescopes have produced mixed results. Some detect faint asymmetries, others none at all. These differences are real but inconsistent, deepening the mystery. As for Psyche, the spacecraft that might hold high-resolution images capable of resolving these contradictions, no such data has been publicly released. Whether these images exist or are being withheld remains unknown. What remains ambiguous? We still don't know how Atlas releases gas without producing a visible dust tail. Its nucleus composition, solid core, loose rubble, or exotic ice mix, remains a mystery. The contradictions between instruments could reflect either a true anomaly
run the next sequence
or
based on these figures.
Bias.
Perfect, that confirms the revised approach.
Electromagnetic or plasma processes play an unusual role is still untested. And as for those multi-wavelength coincidences, such as ASCAP J18-2's rhythmic pulses or the strange bursts of high-energy neutrinos, their connection to Atlas is pure speculation. What is still hypothetical? The notion that Atlas might be artificial or technological remains a provocative idea, but extraordinary claims demand extraordinary evidence, and that evidence doesn't yet exist. The theory that Psyche's data is being deliberately withheld has no proof. nor does the grander idea that Atlas, ASCAP J1832, and other cosmic anomalies are linked by some unified exotic physics. Fascinating as they are, these remain theories awaiting verification. The scientific ladder of certainty. To classify an object as natural means explaining its features through known physics, composition, environment, and structure. To move up to exotic natural requires evidence of extreme but still natural processes, perhaps rare plasma dynamics or novel ice chemistry. Only multiple, independent proofs of deliberate design could justify the label artificial. The path forward: 3 decisive tests. 1. Archival forensic recovery. The most direct step is to access any Psyche spacecraft data that might reveal Atlas's true form. Confirming whether images exist and verifying their authenticity could immediately clarify its nature. 2. Coordinated multi-wavelength observation, a global campaign combining optical, infrared, radio, X-ray and particle detectors during Atlas's next active phase, could capture correlations that single instruments miss. Such data would test whether its behaviour follows natural comet physics or something stranger. 3. High-energy event correlation. By cross-referencing Atlas's activity with neutrino, gamma-ray and cosmic-ray detectors, scientists can determine whether it interacts with high-energy astrophysical processes. A confirmed link would rewrite our understanding. The absence of one would narrow the field dramatically. This is the scientific method at its finest. Establish what is known, test what is unknown, and let evidence, not speculation, determine what is true. Whatever Atlas ultimately proves to be, ordinary, exotic, or extraordinary, it challenges us to look deeper, to question harder, and to refine the very way we see the universe. Let's outline a 90-day roadmap to truly investigate the Atlas mystery. Days 130. Form the Citizen Audit Coalition, a global network of scientists, programmers and legal experts. Divide archival search tasks, file FOIA requests for Psyche mission data, and begin reprocessing all publicly available imagery that might have captured Atlas. Days 30 to 60. Analyse initial findings, submit telescope proposals for a multi-wavelength observation campaign, and reach out to neutrino detector collaborations like IceCube and KM3NET for correlation studies. Simultaneously, launch a public transparency campaign demanding open data from NASA and other space agencies. Days 60-90. Follow up on FOIA responses, publish preliminary results with full transparency, and connect with professional astronomers to coordinate upcoming observations. The mission: turn scattered efforts into a unified, data-driven investigation. How anyone can help. If you code, build search algorithms and validate results. If you have telescopes, observe Atlas during its active windows. If you're a lawyer, assist with FOIA processes and data access. If you run platforms or podcasts, raise awareness, demand transparency. If you can fund projects, support citizen science, data mining and analysis. Every contribution, no matter how small, brings us closer to clarity. We now stand at a scientific crossroads. Atlas's behaviour is strange enough to demand explanation, and for the first time in history, humanity has the tools to find one. The easy route is to label it a weird comet and move on. The harder, but essential, path is to admit we don't know and commit to finding out why. Science thrives in such moments. When nature refuses to fit our models, we either patch the old framework or accept that something deeper must change. Most anomalies fade with better data, but sometimes they crack open entirely new chapters of understanding. We don't yet know which kind Atlas will be. It may be a highly unusual comet, or a new class of celestial object altogether, or, in the most radical but not impossible scenario, an artifact from beyond our solar system. That last idea is improbable, but not impossible. and ignoring it simply because it challenges our comfort would betray the essence of inquiry. The mystery is open. The instruments exist. The tests are defined. Somewhere, buried in archives or in data still streaming from the sky, lies the answer. Discovery doesn't come through easy revelation, but through persistence, collaboration, and the courage to confront the unknown. The Atlas Mystery invites us to practice science in its purest form, to seek truth, whatever it may be. So let's do the work. Let's demand the data, run the tests, and follow the evidence without fear, because the only thing worse than being wrong about the cosmos is having the chance to find the truth and choosing not to look. The frontier is open, the mystery waits, the answer is out there, waiting to be seen.